Welcome back to this lecture series on concurrency state models and design patterns. Today we're going to be looking at asynchronous calls. First, I'll give you a brief introduction to the story of invocation and what kind of asynchronous invocations exist. Then we'll have a look at a number of standard idioms and design patterns for managing asynchronous calls. The first of these is the most simple, that of a relay, where basically you're passing an invocation off to another object, kind of like as we do in adapters. Then we'll look at three mechanisms that appear in libraries and programming languages also as language features, namely tail calls, early replies, and futures. Finally, we'll have just a very quick look at the java.util concurrent library, which provides a lot of standard components and libraries to support asynchronous calls. So first, a quick introduction to asynchronous invocations. So the basic pattern of asynchronous invocations is that you want to avoid waiting for a request to be serviced by separating the act of sending a message and receiving it. So you can apply this in a number of situations. So particularly if the host object, that is the host is the object that's being called, that's providing a service, it can distribute its service amongst multiple helper objects, which can then run concurrently. That's one scenario. When an object doesn't immediately need the result of an invocation to continue doing useful work. So for example, you fork off a task that is performed by some helper, you continue doing some other useful work, and eventually when you need that result, you wait for it. Or when invocations are logically asynchronous, regardless of whether they're coded using threads. So if you have a number of tasks which don't depend on each other, then you can perform these asynchronously. Or if you're refactoring code and you are able to split classes and/or methods in order to increase the amount of concurrency and reduce liveness problems. Here's a generic template that we're going to be using throughout the lecture today, and we'll use it in the example code as well. And it illustrates kind of a generic template of what happens in asynchronous invocations. And we'll see multiple variations of this. So here's an abstract host. It implements the host interface. The host interface is absolutely trivial. So a host is an object that provides a service. And an abstract host has a service method, and the service method consists of four different parts. First, there's some code, pre-code, that is run before the actual invocation. Then there's a point where you call a helper. And while the helper is running, there's perhaps some code that the host wants to run in parallel. And finally, there's some post code. This is what's run after completion of the helper code. Now, in designing an asynchronous bit of code, there's a number of issues that have to be taken into account, and these impact the different patterns that we'll be looking at. So I've listed a few of them here. I don't pretend that this list is complete, but let's have a look at some of these points here. So one question to ask is, does the host need the results back from the helper? If not, then the helper can, for example, directly return the results to the host. So for example, the host passes the task of responding directly to the original caller, and then the host is free to continue doing something else. Can the host process new requests while the helper is running? That could depend on the kind of request. Can the host do something while the helper is running? This means that the invoke helper code is running in parallel with some other during code. Does the host need to synchronize the pre-invocation processing? Is that bit of code synchronized? For example, is the service guarded, or if the pre updates the host state, then perhaps the entire service method may not be synchronized, but just the pre method. Does the host need to synchronize the post-invocation processing? So for example, does the post update the host state? Maybe that needs to be synchronized. Does the post-invocation processing only depend on the helper's result, or does the host have to wait for other conditions? And another concern is the same helper always used? Can we reuse the helper, or do we have to spawn a new helper every time we run the service, or do we have a pool of helpers? So there's a number of issues there that have to be considered. Let's start looking at a number of concrete cases. So we have 4 general groups and some subcategories for each of these. First is the case of simple relays. A relay method is a method that gets all its functionality by delegating to the helper. So that means we only have the invoke helper code. There's no pre, there's no during, there's no post. So this is the absolute simplest case. The host doesn't do very much at all, except passing a task on to a helper. Now there are 3 variants of this case, and they all have some trade-offs. They may seem terribly simple, but there are some subtle issues here. First of all, we can have a direct invocation. So with the direct invocation, we call the helper directly, but without any synchronization. So this gives us some asynchrony for free. Second of all, we may need to create a new thread to invoke the helper. So in this case, we have the main thread, and then we get some asynchrony by creating a special thread for the helper. And the final case is that of a command-based message. So here we reify the task to be performed, turn it into an object. That object is called a command. This is one of the basic design patterns from the Gang of 4 book. So command is an object that represents a task that then can be passed around. So we pass this request to another object, typically by putting it into a queue of commands, and this will be picked up by some other object, a helper or perhaps a pool of helpers, and they will grab this command and eventually service it. So first let's look at direct invocations in a little bit more detail. Here we have an implementation of the host interface. We have a class called host direct relay, and in this case the helper instance variable is final, so it cannot be updated, and as a consequence we don't need to synchronize accesses to it. It's an instance of a counting helper. The counting helper is just a dummy object for the purposes of our demonstration that just counts up to some number. Here we then get some asynchrony by the fact that the service doesn't have to be synchronized. So this is related to the immutability pattern that we saw some weeks ago. So we directly invoke the helper, and then the invoke helper is also unsynchronized code. As a consequence, we get asynchrony. You might wonder, where does the asynchrony come in? By the fact that the host direct relay doesn't have any synchronized code whatsoever, so that means it's able to accept multiple requests in parallel. If the helper is mutable, then we can protect it with an accessor. So here's a slightly different version of the direct relay. In this particular case, the helper is mutable. It can be updated, and in order to access it, we use a getter. So this getter is synchronized, but that's the only thing that's synchronized. As a consequence, we have partial synchronization. To get the helper, this is synchronized code, but to invoke the help method, that part is unsynchronized. Once we've got the helper variable, then we can run in parallel. So as a consequence, calling the service is only partially synchronized, and the moment we have retrieved the helper variable, then the host is available again for concurrent calls. Here's our counting helper. It does nothing except print some numbers from 1 up to a count variable, and from 0 up to a count value. And here's our host interface, our helper interface, and this is our direct relay. Very simple implementation. And if we run that, we can see that here we have 2 hosts in parallel, and running this a number of times will give us slightly different versions of interleaving of the requests being fulfilled. Here's the slightly different version of the host with synchronization on the mutable helper variable. And when we run this, this version is slightly different. Instead of using the count helper, we're using a named helper. This helper has a name, and the name in this particular case is either a dot or a plus. So here we can see that these different these 2 different threads are running in parallel, and all of the calls to the helper are interleaved. Now let's see the variant which uses thread-based messages. Here again we have a host with a helper. All the host does is directly invoke the helper, but in this particular case the invoke helper method starts the helper in a new thread. Here's the implementation of the host with the helper thread. Here again we're using the counting helper. We run it again, and we see the same kind of interleaving as we saw with the other case. In this case, however, we're creating a new thread for every single invocation of the helper, which may or may not be a useful thing to do. So thread-based messages, of course, introduce an additional cost of creating a thread for every invocation. So the cost of evaluating the helper.help should outweigh the overhead of creating a thread. Clearly, that's not the case for our toy example, where we're simply printing a counted value. If, however, the helper is doing a lot of work, heavy computation, for example, then it might be worthwhile. So here are a few cases. So if the helper is a daemon, so a daemon that will loop endlessly, performing various different kinds of tasks over time, or if the helper does some I/O. As we know, usually the cost of I/O overwhelms the cost of any normal kind of computation. There are very few kinds of computation that are very expensive. And possibly if there are multiple helper methods that are being invoked, if it's a complex algorithm. So a typical kind of application might be a web server. As we'll see later today, there is an alternative to creating individual threads. You can make use of a tool, an executor, which manages the threads for you. So for example, if you want to avoid creating far too many threads, instead of managing that self in your application, you can delegate that task to a particular library, which will manage a pool of threads for you. We'll see that a little bit later. Here's another example that illustrates how constructing a helper might be useful if the helper is performing I/O. So here, for example, the host wants to create a new helper to service each request, and we're making use of a file writer which will write some data to a file. So in this particular case, the task of writing to the file is performed in a new thread. Since I/O is usually much more expensive than any other computation, rather than forcing the client or other clients to wait for the writing of the file to complete, we simply create a new thread and spawn that, and then the main thread is immediately available to service other requests. The last example in this group is that of command-based messages. So in this particular pattern, instead of having a simple relay with no synchronization or creating a thread or using a pool of threads, what we do instead is we reify the task by turning it into an object. Reification means taking something that's virtual, turning it into an object. So the task, the message, becomes an object, and this is known as a command object. This is, as I mentioned earlier, one of the basic design patterns in the Gang of Four Design Patterns book. Here we see its use in the context of concurrency. So the host, at the point where the helper should be invoked, instead of directly invoking the helper here, what we do is we create a new object, which is a runnable object. So the host here, instead of directly invoking the helper, what it will do, so here we have the invoke helper method, what it will do is it will place a command in an event queue where this command will be read by some other object, eventually the helper. The object that's being put into the queue is a runnable, and the run method is the method that will actually invoke the helper. This is typically useful for scheduling of helpers when we have a pool of threads. As I mentioned, we'll see a little bit later that there are standard libraries providing management of pools of threads. It's also interesting if you need to undo or replay commands. So in this particular case, you would need a command that you can not only do, but also undo. And if you have, for example, a transaction that needs to be undone, if you keep track of all of the commands that are performed, if at some point you have to abort the transaction, you can simply go through the commands and tell each one of them to undo its action. Another reason for turning tasks into objects is then that way you can send them over a network to be performed at a different logical site. We've done now with the first basic pattern of simple relays and its three variants. Now let's have a look at tail calls. So a tail call is a special situation when the helper method is the last statement of a service. So we have no post code, we have a pre-code, and the only code that needs to be synchronized is the pre-code. So the host starts executing in its service, it has some pre-code which will possibly update the state of the host, and then we reach a point where the helper needs to be invoked. Here's an example, a tail call subject. So the tail call subject is an observable object, and it has an observer. It has a state which can be updated, and the update method is the service that's being performed, so update state. And it consists of two parts. The first part actually performs the update, and the second part sends a notification, that is, it updates the observers. And notice here that the service consists of two parts, only the first part of which is synchronized, or partially synchronized in this case. So the update state method is unsynchronized. The do update is a synchronized method, and the send notification is purely unsynchronized. So this is where we get a certain degree of additional asynchrony. That is, when the update state method is called, the pre-code, namely the do update, is synchronized, so the host, the tail call subject, is locked, and then when that is completed, then we proceed to the invoke helper code, which is in this case the send notification, and that is purely unsynchronized. So at that point, the host becomes available for another service. A variant, similar to the variant we saw earlier, is instead of having the tail call be completely unsynchronized, you could also perform it in a separate thread. Once again, you have the same concerns. So only create a new thread if there's a considerable amount of work to be done, because the cost of creating a thread, if that is as high as or higher than actually invoking the helper code, then there's no advantage to be gained. The next pattern has also been implemented as a programming mechanism in certain programming languages. It's the notion of an early reply. So the idea of an early reply is that the host is executing some code, and at some point it's ready, it has a result that it's ready to return to the client, but it has some additional work to be done. For example, some cleanup code. So what you would like to do is not return, but reply. So the reply is like a return in the sense that it actually returns something to the client, but it doesn't terminate the executing method. You can have additional code following afterwards. Normally, in most programming languages, with a return, you cannot have any code following the return. So the reply is similar to a return, except it does allow you to do something afterwards. However, clearly Java does not support early reply, so we have to simulate it. The key thing is that we have to somehow retain synchronization. So we need a way of having a host that is executing a method. Somehow we need to be able to return something, but not give up synchronization. So it's not enough to simply spawn off some separate thread. We want to make sure that the return and the additional thread is going to be performed within the same bit of synchronized code. So let's see one possible way of doing this. So I can imagine there are various ways of realizing something like an early reply in Java. Here's one possible solution. We're illustrating this as a UML scenario diagram. In this diagram, we have a host and a client. The client makes a request, and the host is going to perform an early reply. The key idea is that at the point that the early reply takes place, the client and the host can continue executing in parallel. So that's where the asynchrony is coming in. The host maintains its synchronization, so no additional clients can come in until the cleanup action is performed. Well, how can we manage this? The key idea is to make use of a one-slot buffer. So the one-slot buffer is a buffer that you can put something and get something, but if there's something already there, you can't put something else. And if it's empty and you try and get, then you're forced to wait. So the host creates a one-slot buffer and creates a helper, and the helper has access to the slot. We then start the helper, and the helper at some point in time produces the result, places it in the slot, the host gets it and can return it. The helper then can continue executing after this point. Of course, the key thing is any synchronization that we need to keep on the host should still be there. So here's some skeleton code, actually running example that illustrates how this could be done. Here's our early reply demo. We're providing a service. And in this service, we create a new slot. We also create a new thread and start it, and this is our helper. And in the run code, we maintain the synchronization of the host. So this is where the service is actually performed. Notice that the service itself is not synchronized, but this is the code that's actually executed for the service, and it consists of two parts. We compute something, and we reply. We reply by placing the result in the one-slot buffer. This essentially affects the early reply, and then we can continue performing our cleanup action, still maintaining the synchronization on the host. The client gets the result, because here we're waiting for the result in the one-slot buffer. As soon as we get it, we return. So this is where the early reply actually takes place, but the cleanup action running in this thread maintains the lock on the host until we've finished the cleanup, and at that point in time, a new invocation of a service might be able to get in. Here's the demo of the early reply. It's constructed exactly as we saw on the slide. So we have our service here. The synchronization is only occurring on the host within the run method. And the early reply happens once we get the result. The actual work is done in the computation, and we have a cleanup. The computation in this particular toy example is to perform a random sleep to simulate some heavy computation, and it just computes and prints out a factorial. The actual cleanup is an action that in general could be computationally expensive. Here again, all we're doing is we're printing out the fact that we're cleaning up, and then we finish cleaning up. Just to illustrate that we do not actually have any possible interleaving issues, we perform a thread.yield, but since we're retaining the lock on the host, this will not allow any other threads to come in. So we can see in the results that this is actually the case. We perform random sleeps, and here in our main thread, we're going to start up 3 demo threads computing factorials from 4, 5, and 6. And when we execute this, we can see that the services are being called to compute the factorials of 4, 5, and 6. And the result can be computed. We perform some cleaning up. This cannot be interleaved with anything else, and the client has gotten the result. If we run this multiple times, we'll see various possible interleavings of these results. And in no case will the cleaning up and the computation interleave with any other actions. So this is exactly what we expect. So the host is completely protected transactionally in this bit of code. The final pattern that we're going to look at is actually much more common nowadays than early replies. So early replies are a little bit esoteric, actually a very elegant mechanism, but they've not been supported in very many different programming languages historically. Futures, on the other hand, appear both as libraries, library components, as they do in Java, and also as programming language mechanisms built into various languages over time. The idea of a future is to allow a client to continue in parallel with the host until the future value is needed. A future is essentially a ticket. So think of yourself going to the butcher, and you want to order something and say, okay, I'll pay for this now, and I'll pick it up later when it's ready. And then you can go to another shop, go to the baker, order some things and say, hey, can you please prepare that for me? You pay, you get a ticket. Then you go back to the butcher, ask for the package that you've ordered. If it's ready, you get it immediately. If it's not ready, at that point you wait. Then you go back to the baker and you say, here's my ticket, here's my future. Is it ready? Yeah, here it is. And then I can pick it up. So the key thing is that the client immediately gets a ticket for the future, and the client can continue executing until, that is doing something in parallel while the future value is being computed, and then only when the client actually needs that value will the client block. So here the client issues a request to the host creates a new future and returns it to the client. then the host can continue executing, and at some point the host will produce the value that is needed in the future, and the future at that point will get initialized with the value that the client is waiting for. The client at some point asks for the value. If the value is not there, then the client will block and wait. So if the client here starts asking before the host has actually produced the value, then it will wait until that point in time when the future is available, and then it will return and they can execute, continue executing. Notice the asynchrony occurs in between the time that the client obtains the future and the point in time when the client wants the result of the future. So here's a possible design of a future class for Java. Here, future is designed as an abstract class, a generic abstract class with an argument and a result type. The future, when it's initialized, when it's constructed, a new thread will be created to execute, to start the run method. And what the run method does is it sets the result, here's the set result method, to a value of a compute result method, which is abstract. So in order to make use of the future here, you would create a subclass of future which would implement the compute result method. What happens in this thread, the result is computed and then it's set in a synchronized method, and a client that wants the result asks for the result. This is the point where we would wait. So if the result is not been initialized to any real value, if it's still null, we will wait. The moment that the value is computed, presumably that value is not null, then the result gets assigned. We notify all the waiting threads and return. At that point, any client that's waiting for the future will be woken up and it will get the result. If we have multiple clients waiting for the result, after the first future value has been set, then all of these threads will wake up and be able to access the result. So here's a little bit of Java code illustrating how we could use the future in order to avoid defining a subclass of a named subclass of the abstract class future. What we do here is we make use of an anonymous inner class. So we create a new future that implements the compute result. And what it's doing in this case, just to show an example of something that is a little bit more computationally expensive, is we have a naive implementation of Fibonacci, which is multiply recursive. That is, it's going to be exponential in the size of n. So here's our demo example. We have our future class. We have the constructor, which will start a new thread to compute the result and set it. The compute result method is abstract. Set result and obtain result are synchronized. Here we have some demo code which will run a demo thread to compute Fibonacci's of 35, 25, 15, and 5. And here we instantiate our future with an anonymous inner class that computes the Fibonacci results. And if we run this, remember we're starting with the highest Fibonacci going down to the lowest, and we can see that we are creating the Fibonacci's in an unknown order because we're creating these threads in parallel. And we get the futures, but the order in which we get the futures doesn't correspond to the order in which the results are computed. So you might have expected that Fibonacci 5 would be being computed first, but it depends entirely on how these threads are scheduled. So every time we'll run this, we'll get a different possible ordering, but as you can expect, Fibonacci 35 is pretty much guaranteed to be the slowest and the last one to be returned. Well, that completes the first part of this presentation, or the main part. We've seen several design patterns for achieving asynchrony in concurrent designs. Now, I just have a few slides to end up with. I'm not going to go into them in any particular detail. My goal is not to teach you Java libraries, but just to raise some awareness about what's available. So there is a library called java.util.concurrent, and it provides a lot of components and features which are particularly useful if you are building concurrent applications, and particularly if asynchrony is an issue. The library is rather large. Here are some of the main parts of it. There are so-called executors, which are objects that manage execution of concurrent threads. We have various kinds of queues for managing queues of objects and commands, for example. We have various concurrent collections, which are guaranteed to be safe guaranteed to be thread safe. Various kinds of synchronizers, so these are objects that are useful for declaring and managing critical sections. We have also various kinds of locks, and also some mechanisms for defining atomic blocks. The executors are especially interesting because they provide a means of managing thread pools and also provide futures. I've mentioned a few times already that you have to be careful if you have code that creates new threads, particularly if you're creating new threads for each service that's performed. Because if you have no bounds on the number of threads that are created, this may lead to performance problems. The idea of Java util concurrency is that you have executors which will manage pools of threads for you. So you can specify, for example, that you would like a pool of a certain number of threads, and then when you have a task to be performed, it's passed to this pool of threads. Essentially, your requests will be queued up, and as soon as the thread is available from that pool, it will get executed. I've already mentioned we have concurrent collections. There are queues and blocking queues, concurrent hash maps, and so on. So these are all different forms of thread-safe collections. We also have different kinds of locks and conditions. Read-write locks we'll be seeing in very soon in an upcoming lecture about read and write conflicts and how to manage them in code. So there are particular components here designed to help with that. We also have different kinds of synchronization mechanisms. We've heard about semaphores, but there are other mechanisms like latches and barriers. A latch, for example, is like a future in that once it's set in a particular setting, once it's open, it stays open, or once it's closed, it stays closed. And the atomic variables, they're used for writing lock-free algorithms. The executor framework is probably the most useful of the components in this framework, or the one that you should pay most attention to. So this helps you in managing asynchronous task execution. We've already seen and we're familiar with the runnable interface. The executor framework also adds a new thing called callable. So callable is like the run interface, except it will return something. So callable interface is parameterized with the value type of what is returned, and it can potentially throw some kind of exception. The key thing is that when you want to separate the submission from the actual execution policy. So there are different executors that support the same interface, but you can plug and play. You can swap in different execution policies, different implementations of executors that adhere to different policies. So particularly if you want to have different ways of managing your thread pools. They also provide support for canceling threads and shutting down. For example, if you need a lot of helpers to perform some computation, once you've got the first result back that's acceptable, you can shut down the remaining ones. The executor decouples the submission policy from the task execution by providing a standard interface. The interface simply says, let's execute this runnable command. The code that submits the task doesn't have to know in which thread the task will run. That's very nice because you can then implement very generic code, and then only in the code that configures the setup of the executors can you decide which policy, which particular version of the executor you'll instantiate and plug into your application. Executor service is another interface that extends executor and provides some lifecycle management. Here we can see, for example, we can tell the service to shut down or shut down now. We can ask if it's shut down, and so on. There are also some useful utility methods, for example, to execute given tasks, returning the result of one that completes successfully, if any. So invoke any. I showed you earlier a possible implementation of a future as an abstract generic class. This is not the one that's implemented in JUC. JUC also provides a future called future task. It's a generic implementation of futures, and it's parameterized by callable or runnable services. Here's an example. We have a service here, and this service is going to return a future task of type integer. Here we initialize the future, and we create a new future task and pass it, when it's created, a callable. And the callable will execute our Fibonacci code. Then, once we have the future, we start it, and then we return it. So in the earlier implementation, when we construct the future, it created and started a thread immediately. In the version provided by JUC, you create the future task and then afterwards explicitly start it. Notice if you're using JUC anyway, instead of starting the future in a thread, what you can do instead is make use of an executor. Here we see the JUC equivalent of the example that we saw earlier. We're going to compute the Fibonacci's of 35, 25, 15, and 5, except instead of using our abstract future class, we're going to plug in the future task from JUC. So here we create the new future, and the future passes in a callable. The callable will return an integer value, and it will compute it by computing using our extremely slow exponential Fibonacci program. Once we have the future, we will create a new thread using that future, because the future has a run method to execute it, and we return that future. Once we pick up the future, we will wait for its result. And as before, we will create 4 demo threads to compute these 4 different values in some arbitrary order. This will happen, and then in some other arbitrary order, we will get the results back when the so we get the futures quite quickly, but we will have to wait, and typically the Fibonacci 35 is going to be the last one returned. Here's a few examples of different executors that are available in JUC. There's a new single thread executor. It has a pool of 1 working from an unbounded queue of tasks coming in. There's a fixed thread pool, so pool of n helpers, again working from an unbounded queue. A cached thread pool, so you have a variable size pool that grows as needed. And a scheduled thread pool for executing tasks after a given delay or on a repeating basis. There are various locks and synchronizers provided. I won't go into any details here. I encourage you to have a look at the JUC documentation. And there's also the very good book by Baubier and colleagues describing, which teaches you how to write concurrent programs in Java, especially using JUC. So that concludes everything that I wanted to show you this week. Thanks for your attention, and see you soon at the interactive session.